Good morning, students. Welcome to the lecture series on signals and systems. Today, we are going to start with a new topic uh, called as signal analysis. This might be a first lesson in our journey of characterizing the signals. Until now, we have dealt with many basics related to signals, such as what are the classifications on signals, what kind of operations that we perform on signals, and what are the elementary signals that are available, and how we deal with them. But now we are going to study about a signal and its analysis. How do we represent a signal with respect to another? Okay, how do we represent from one domain to another domain? So it serves, this particular discussion serves as a basic for the futuristic analysis of signals. It will be very easy to understand or remember anything new whenever we compare it with or whenever we associate it with the familiar things that what we already know. So while studying a new problem, generally we search for analogies between that problem and also and a familiar phenomenon that we already know. It will be always good, and you can gain some insight whenever you compare with the already existing phenomena for this new problem. So this can be already done. You might have seen in another subjects there where we can actually derive an analogy between the electrical systems and mechanical systems. Okay, we are familiar with the electrical systems, and mechanical systems can be easily understood by using the analogy between them. Similarly, now since signal we have defined the signal as a physical quantity which varies with respect to a set of independent variables. That means signal generally have some direction in the direction which they travel, and it also has some magnitude in order to travel through particular directions. In mathematics, we know a concept called as a vector. A vector is also specified by magnitude and direction. Therefore, now what we shall do is, as there is a perfect analogy between vectors and signals, we shall use this analogy between vectors and signals and try to understand the signal analysis in a better way. Okay, we shall start with vectors. With this little introduction, now I would like to just revise the knowledge that what we have in vectors, and let us try to compare with try to analyze with respect to the signals there. As I said that a vector is specified by magnitude and direction. We shall always denote all the vectors by some capital letters or the bold-faced letters, and their magnitudes generally we represent it with. Okay, let us consider this representation. Generally we use for representing a vector, and generally we represent a light-faced letters generally in order to represent the magnitude of that vector. Now let us try to analyze or representing a vector something like v1 in terms of v2. Let us consider here v1 is a known is an unknown vector, and v2 is a reference vector. That is a known vector through which I would like to measure the v1. Okay, I would like to just assess this v1 in terms of v2. So let us consider the two vectors are traveling in these two directions. Let us consider this is v2 and they have the same origin, but they are traveling in different directions, v1 and v2. The vector v1 can be expressed, this vector v1 can be expressed in terms of v2 in infinite ways by drawing a line from the tip of this vector onto v2. This can be drawn in this way, or this can be drawn in this way, or any other ways. You can draw, always you can draw some another ways. Okay, so there are infinity ways of drawing v1 onto v2. Why we need to generally do this? In each representation, generally v1 is represented in terms of v2 plus another vector, which is what we call as error vector. These are called as error vectors. You can represent your v1 in terms of v2 by using these error vectors. Okay, these are different error vectors that can be possible whenever you try to draw this vector from the v1 to v2. Here, whenever we clearly see this particular figure, v1 is approximated by v1. Now I am trying to approximate my v1 in terms of v2. Therefore, I just represent that it as v1 can be approximated as some component of 1, this vector v1 with respect to v2 multiplied by v2. Okay, they represent some magnitudes. I'm just saying about the magnitude of v1, which is expressed in terms of v2. This c12 actually says about the component of vector v1 along v2. Just as what we say, it is 2 times of this vector, or 3 times of this vector, or 0.5 times of this vector is this one. So I'm trying to assess the magnitude in terms of v2 now. In order to have a better approximation, generally we say that it can be equated with considering the error vector also. Okay, therefore v1 is equal to c12 v2 plus ve, where ve represents the error vector. Okay, so similarly you can represent with respect to all these vectors also, ve1 or ve2 or ve3. You can always write your v1 in terms of c12 v2 plus ve1, or either ve2 or either ve3 or so on. Okay, you can, since there are infinity ways possible, you can always say that you can always represent in any in the form of any vector, any error vector. But v1 is approximated by c12 v2 with an error vector ve, where as v1 is equal to c12 plus v2 plus ve. Geometrically, whenever we consider geometrically the component of a vector v1, geometrically, if at all I draw this, I say that geometrically the component of a vector v1 along v2 is obtained by drawing a perpendicular. By drawing a perpendicular from the tip of v1, from the end of v1 onto v2. In this case, generally the error vector is going to be minimum. The component of a vector v1 along this another vector v2 is now given by c12 v2, and this ve is a error vector minimum possible in all the cases that we generally see. Okay, there might be infinite ways possible, but however, this is the way where this error vector will be minimum. If this error vector is minimum, you can say that this v1 can be approximated better in terms of v2. Okay, and we generally see that the error vector should be minimum, and only when we draw a perpendicular, in that case that error vector will be minimum. Now I choose a c12 value. I choose a c12 value such that the error vector has to be minimum, satisfying this particular equation. And the magnitude of c12 is an indication of the similarity of those two vectors v1 and v2. If c12 is equal to 0, then this vector v1 has no component along the other vector, this v2, and hence two vectors v1 and v2 are mutually perpendicular. We generally say that this v1 and v2 are mutually perpendicular whenever the c12 is equal to 0. Let us see this case by using this graphical approach or this geometrical approach. This is the only possible case whenever you can't draw a tip from this vector onto v2. because whenever you try to draw a perpendicular, this becomes a parallel line. This error vector becomes a parallel line onto V2, and this never meets V2. Therefore, this component can be never assessed in terms of V2. This V1 can never be expressed in terms of V2. That is the reason I say that this C12 is equal to 0. If C12 is equal to 0, that means V1 cannot be assessed in terms of V2. And you can say that this V1 and V2 are mutually perpendicular. These vectors which are mutually perpendicular to each other, they are generally called as orthogonal vectors. They are called as orthogonal vectors. Orthogonal vectors are also thus independent vectors. They never depend upon any other vectors. Okay, they can also be called as independent vectors. So from the knowledge of vectors, now I would like to express this orthogonal vectors such that if the vectors are orthogonal, then the parameter C12 is 0. Generally, as from the knowledge of these vectors, the component V1 along V2 can be expressed in terms of dot product, and we can write that it as, okay, these are vectors V1 and V2, and I'm trying to obtain the dot product. And if at all you would like to represent the component of V1 along V2, then we generally write it in terms of V1 dot V2 by V2. Or, so this is what we have said as C1 to V2. Okay, we have denoted it with the C1 to V2. In the case of in the above discussion, we have generally said that the component of one vector along the other can be expressed as C1 to V2. Therefore, in this case, now I can just represent my C12, that is a component C12, can be expressed now as V1 dot V2 by V2 square. I have brought this V2 this side, and therefore I have expressed it as V2 square. Or else this can also be represented. This can also be represented as V1 dot V2 by V2 dot V2. As we know that whenever we perform, the dot product between any two vectors is given by AB cos theta, where theta is the angle between those two vectors, and A and B represents the magnitude of those vectors. Okay, these two are vectors, and we represent it in terms of magnitudes and their angle between them. This dot product is generally given in this way. If you are trying to find out the dot product between two vectors, that means which are the same vectors, then it becomes simply A into A. Okay, this is simple multiplication of their magnitudes and the cos theta between them. That is the theta between them. Generally, if you are considering the angle between the same vector, then this becomes 0. Therefore, cos 0 will be represented as 1, and therefore this will be simply equal to magnitude square. That means A dot A, the dot product between the like vectors, is given by magnitude square. I use this particular formula in order to represent here. The V2 square is generally represented as V2 dot V2 now. Here V2 is considered to be vectors. And when vectors V1 and V2 are orthogonal, when vectors V1 and V2 are orthogonal, or AB are orthogonal, generally as said above, if AB are orthogonal, they can be considered to be mutually perpendicular. Therefore, this theta becomes now 90 degrees and cos 90 becomes 0. Whenever I multiply this A dot B, the magnitudes of AB with 0, this results in 0. Therefore, the dot product, whenever AB are mutually perpendicular, they becomes 0. Therefore, for orthogonal vectors, you can simply consider the dot product is 0. Therefore, whenever V1 and V2 are orthogonal, this dot product becomes 0, and as per our discussion, that C12 also becomes 0. That means this actually verifies that what we have actually said above. Okay, that means C12 is still equal to 0. Now, these kind of analogy can be adapted for signals, and let us also assess one